In this lecture, we're going to start talking about the column generation technique. The first part of the column generation technique is a reformulation of our integer program. If you need to remind yourself about exactly what integer program we're going to be working with, you should consult the previous lecture. In this lecture, we're going to focus on this set, capital Xi. And we're going to write capital Xi in a completely different way. Initially, capital Xi is defined as the set of all vectors Xi that satisfies some linear constraints. But now we're going to write Xi as an explicit enumeration of all of the feasible points. In this case, the feasible points are all the vectors that satisfy this linear constraint. We're going to assume that there's capital Ti of these feasible points. This explicit enumeration is going to be key for the Dantzig-Wolfe reformulation. To see how this formulation is going to work, we go back to our initial ideas about how feasible sets are formed. In this case, we have our set of points, capital Xi, and those are the blue points labeled. We have our set of linear constraints, dixi, and in this case, we've said that the dixi are going to be this linear constraints associated with the pink polytope, or polyhedron. We also drew in the graph the convex hull of the set capital Xi. The convex hull is the set of all points that are going to be linear combinations of the points Xi. Just to be clear, in this case, the value capital Ti of the set of feasible points is 7, because there's 7 feasible points, feasible blue points inside of this region. The key to the Dantzig-Wolfe reformulation is to think about how we can write the convex hull of capital Xi. One way we could potentially do it is how we've thought about it before. We can write exactly the right constraints that's going to define the convex hull of Xi. We've seen that there can potentially be an exponential number of constraints in this case, but there can be all sorts of other problems too, most notably that we don't know exactly how to write the convex hull of Xi. The Dantzig-Wolfe reformulation idea gets around this and gives us an explicit way to write the convex hull of Xi based on the explicit enumeration xit. In this case, we can write any point inside of the convex hull of X as a linear combination or a convex combination of the points xit. Here, the multipliers to this convex combination are going to be lambda t. If you're not familiar with convex combinations, a convex combination of points is a linear combination of points where the linear multipliers sum to 1. Effectively, the convex hull of X can be defined as any convex combination of the feasible points inside of capital Xi. Unfortunately, writing the convex combination or the convex hull of Xi isn't going to be of particular use to us in reformulating an integer program. Notably, the convex hull of Xi includes some points, for example, this one, that doesn't land on any integer lattice. So this is going to be a non-integer point. Instead, we need a formulation for capital Xi, but it turns out that this is actually very similar and particularly trivial. In this case, what we need to do is again write a convex combination of Xi, limit our multipliers to be convex, that is, they sum to 1, but instead of having them slide over a range between the values of 0 and 1, we force the multipliers to be either 0 or 1. It's easy to see that when we do this, combining the 0-1 constraint with the sum to 1 constraint, that exactly one of the xits is going to be chosen. Although this seems like a pretty strange way to write capital Xi, it turns out to be very useful. In effect, this formulation is going to pick out a particular feasible point, and we don't know which one is going to be picked a priori. The Dantzig-Wolfe reformulation combines our previous program, our decomposable program, with this new idea, writing capital Xi as some linear combination, and gets us the Dantzig-Wolfe reformulation. The key ingredient to this is rewriting the vector xi, little xi. we can rewrite the vector little xi as the sum from t equals 1 to capital Ti of xit times lambda it. Here we've introduced a new index for our lambda. Recall that when we looked at the Dantzig-Wolfe reformulation idea, we were talking just about lambda t's. Now we're talking about lambda it's. We're going to have a set of lambdas for every index I, remembering that this index is an index over the decomposable sets. This key reformulation idea is effectively telling us that our vectors in our decomposable program, the xi's, can be written as a convex combination of the feasible points in capital Xi. This convex combination is restricted so that each of the multipliers, the linear multipliers, is either 0 or 1. Effectively, this is telling us that Xi has to be equal to one of the feasible points inside of our feasible set, capital Xi. Now we take these ingredients. We take this idea that Xi is being chosen out of the set of feasible points, capital Xi. We combine this with our decomposable program, and we write a new program. This new program rewrites all of the Xi's as the sum over all t of xit lambda it. This is just using this equality down here that we've derived by reformulating capital Xi. We substitute this quantity in the objective function, the link constraint, and now we don't have any other constraints to do any substitution. Instead, we're going to write the convex constraint for each of the i's, and then write the constraint that these lambda i's has to be equal to 0 or 1 as an additional constraint. What we've done is a substitution for xi, and then included the additional constraints required to define these lambda multipliers. Now when we look at this new program, we should note something. Although we see these potential variables xit, xit actually is no longer a variable. Xit has been an enumeration of all the feasible points in capital Xi. Each one of these xit's we know explicitly, and so it's a constant. The only variable in this new program is the lambda. We inherit this variable lambda from this new program, or rather new definition of capital Xi. And so what this reformulation technique has done is it's replaced these variables, these vectors xi, with a new set of variables, lambda I, by explicitly enumerating all the feasible points and writing the xi vector as a linear combination. This is the key of the Dantzig-Wolfe reformulation. We've taken some decomposable program written in variables xi with a link constraint. This link constraint is potentially difficult to handle. What we've done is we've expanded the number of variables considerably. We now have a set of variables lambda I, and there's one of these variables for every feasible point in each of the capital Xi's. The number of lambda i's is very huge. It's enormous. Initially, this huge number of variables doesn't seem very helpful, but we're going to see that we can use this huge number of variables to our advantage in the future. For now, we're going to look at a potential way to reformulate, or rather, develop new notation for this reformulation. Our new notation is going to vectorize all these quantities. Now we're going to write Ci xit, which is actually a multiplication of a lot of constants, as a vector, C. And although we've written this as just C, we have to recall that this C depends on two things. It depends on the constant C in our initial problem, and also these new constants associated with feasible solutions in capital Xi. We multiply this vector c times the vector lambda. This vector lambda includes the terms for all I and for all t. This is a huge vector. We do the same thing for the matrix A, including the terms for ai xit in a new term, capital A, and multiply this by the vector lambda and set this less than or equal to b. Finally, we write the constraints associated with the convexity, or the convexity, as a new set of constraints, e times lambda less than 1 or equal to 1. In this case, this is the number 1, but this is a vector of 1s. We've introduced a new vector of 1s. And we've multiplied our vector lambda by a new matrix E that we've defined here. This new vector E is going to be something like an identity matrix, except we think of it as a block diagonal matrix. In each one of these blocks, we have a vectors of 1s. There's a number of 1s equal to the number of variables, or the number of lambdas, which is equal to the number of feasible points in Xi. Along this diagonal, we have a vector of 1s, one vector for each of the sets 1 through k. It's not particularly important exactly how to define this vector or matrix E. What's really important is that we're going to just compact our constraints that tell us our lambdas have to be convex into some easier notation to digest. Note that we've retained the fact that lambdas are our only variables. In this case, lambdas come from a 0, 1 vector with dimension capital N. Capital N is going to be the sum of all the feasible points over all the capital Xi's. This N is an enormous number.